So we are covering continuity over more than just today. But I have the definition of continuity at the top in that top box. And so it says a function f is continuous at a number a, and this a value is an x value. So a function f is continuous at an x value a if this limit is true. So if the limit as x approaches a of the function f of x is equal to f of a. So to point out with this equation that we have here, so the left side is the limit as x approaches a of f of x. So what are the y values approaching? F of a is actually the function value at the x value a. So if you remember from that Desmos activity, it gave a very general definition of continuity, and it said that the limit from the left, the limit from the right, and the function value all had to be the same. And that is what this definition is stating. In order for the limit to actually exist, the limit from the left and the right have to equal the same value. And in this case, it's saying it has to equal the function value. So the limit from the left, from the right, and the function value all have to be the same at the value a in order for it to be continuous there. So just a general sketch of what this could look like. Say this is our x value a. I'm just going to draw a general curve here. And then this here would be f of a. But you can see there's no hole in the graph there. So if I'm approaching the x value a on either side, both sides of my curve are approaching that same value, and it does happen to be the function value. The function does exist at a, and it's equal to the limit. So another way to really think about continuity, and this is where I said the definition of continuity just makes sense. A continuous curve is one where you could trace along the curve with your pencil and never have to lift your pencil. So you're not lifting your pencil because there's a hole, or you're not lifting your pencil so that you can jump to a different part of the graph if there's a break in the graph. So no breaks in the graph, no holes, no asymptotes, nothing like that, then it's continuous at specific values or on intervals. So we'll always come back to this idea, but if you ever have to prove a function is continuous at a value, this is what you have to show. So if you ever have to prove continuity, this is what needs to be shown, that the limit and the function value are the same. So these are the three requirements. I've already kind of talked about them. First of all, in order for this equation to be true, f of a has to be defined. So a has to be in the domain of f. The limit has to exist, meaning that the limit from the left and the limit from the right are both equal to each other. And then the limit and the function value actually have to be equal. So that's a more formal list of requirements for continuity than you saw in that Desmos activity, now that we know more about limits. So then I have here, sometimes it's easier to understand what something is when you have a visual of what it's not. So there's three ways, if there's three requirements for a function to be continuous, that means there's three ways a function can be discontinuous or not continuous. So if we say f is not continuous at a, we can say it's discontinuous at a, we can say it has a discontinuity at a, so those are different phrases you'll see. And like I said, there's three different ways in which it can be discontinuous. The first way would be if this first point is false, so if f of a is not defined, meaning the function may not be defined at a. So I'm going to try to draw a similar curve up here so you can kind of compare the three. This would be the continuous one. So here if I drew a similar curve, say this is a, what this would look like is if in my function I had a hole in the graph there. So there's no actual value of the function at a. There would just be a hole in that graph. So notice in this case, the limit still exists. The limit would still be whatever this value is here, but the function value doesn't exist. So then the second way it could not exist would mean that second point above isn't true, so the limit could not exist. So in this case, say this is a, so this graph will look a little different. Say I have this piece of my curve, and then this is the second part. So notice I did draw it so there is a function value. Where this dot is, I would have a function value at a, but now the limit from the left and the limit from the right are different. So the limit at a doesn't actually exist. And then the third condition would be the limit exists and the function value is defined, but they're not equal to one another. So I could draw this, yes. So I could draw this same graph I drew for part A. But then I have a hole in the graph, and then maybe I have a dot here. So this would be f of a, but where this hole is, whatever that y value is, that would be the value of the limit. So they both exist, they're just not the same. So we are going to go through some examples, and the first sets of examples are going to be finding values at which a function is discontinuous. So in looking for discontinuities of a function, you're looking for one of these three things to not be true. Either at this x value, the function doesn't exist, the function value doesn't exist, the limit doesn't exist, or they don't equal each other. So example 1, and I know I've said this before, these graphs never copy the greatest, but we have the graph of a function, and it says at which numbers is f discontinuous and why. So in this graph, this here, so this should be an open circle. At 3, you're going to have a dot on the lower part, circle in the upper part. And then at 5, this is hard to see. There's a circle on the curve, and then it kind of looks like an accident, like there's a little smudge. This is actually supposed to be a point up here. I apologize for the not greatness of the copying. Yeah, that would be a better way to say it. The low quality of the copying, yes. All right, so in looking at this, what is an x value you would say at which this function is not continuous or is discontinuous?
1.
At 1, okay, x equals 1. And then y. So which of those three requirements is not met at the x value 1? Why is it discontinuous there, okay? It's not defined at 1, yeah. So we can say it's discontinuous at x equals 1 because f of 1 is undefined. There's no function value at the x value 1. All right, what's another x value at which this function is not continuous? 3. Okay, so at x equals 3, it's discontinuous because, and I could actually just say, I could certainly say the limit from the left at 3 does not equal the limit from the right, or I can just say the limit as x approaches 3 of f of x doesn't exist. So some of you had this question or reviewing for your quiz in terms of reasonings. In this case, I don't need to specify that the two one-sided limits aren't equal. I can just say the limit doesn't exist. If I was explaining why the limit doesn't exist, then I would have to say because from the left and the right, they're not equal. And then the last value where it's not continuous, at 5, it's also discontinuous. And what reason will we use at 5? Yes. So here the limit exists. It's whatever this y value would be. The function value exists. They're not equal to each other. So the limit as x approaches 5 of f of x does not equal f of 5. And notice, especially when I'm writing out these limits, I'm not writing out in words the limit as x approaches 3 doesn't exist, or the limit as x approaches 5 doesn't equal the function value. If you're writing it into words, yes, that's correct. That's not going to earn you credit on the AP test. They're looking to see that you understand and can write the notation. So you need to have that notation. Practice using it. Okay, any questions from a graph? Now we are going to answer the same types of questions, but now these functions are given in their algebraic form as formulas or equations, not as a graph. And you need to be able to determine where a function is discontinuous without looking at the graph, because remember, you won't always have a graphing calculator available to you. So if we look at A, taking a look at this function, does anything stand out to you in terms of where this function might not be continuous? And why at 2? Okay, so if we just find the domain of this function, looking at the denominator, I know x minus 2 cannot be 0, meaning x cannot equal 2. So if x is equal to 2, the function is undefined because I'm going to have 0 in the denominator. So I can say this is discontinuous at x equals 2 because f of 2 is undefined. That's all you have to write. So looking at that function, that's really the only place where this function isn't going to exist. It's kind of like finding that domain. We know the x value can't be 2, but x could be anything else. At 2, though, it's undefined, so that will not be continuous there. Then for B, now when you have a piecewise function, and this was kind of already talked about more so with some of you that were asking questions with the review. You're checking at the value where the domain has a break, or rather in this case at 0, depending on the values at 0 or surrounding 0, the expressions are different. So this gives you a hint that you should check for continuity at the x value 0. It's going to be continuous elsewhere, but if x is 0, you should check to see if it is continuous. So first of all, would you say that f of 0 is defined? Is there a function value at 0?
Yeah.
Yes, what is it? 1. So I'm just going to write that down. F of 0 is 1. So that's defined. So I'm kind of going through those 3 checkpoints. Does it have a function value at 0? Yes, it does. Next, I should check to see, does the limit exist? So to check if the limit exists, I'm not focusing on the 0, 1 part. I'm focusing on the expression 1 over x squared. So I should find the limit as x approaches 0 of the 1 over x squared and see if that limit exists. So I can use direct substitution. If I use direct substitution, I'll have 1 over 0 squared, so 1 over 0. That's undefined, so this limit doesn't exist. So I can stop there and say this is discontinuous. I'll actually write this one out because I know I have other work shown here. So it's discontinuous at the x value 0 because the limit as x approaches 0 of f of x does not exist. Questions there?
You don't have to put specifically like the limit of 1 over x squared.
No, if you did, that would be okay, but in general, the 1 over x squared is just part of the function. So if I'm taking the limit as x approaches 0, I'm using this expression, but that's really the limit as just x approaches 0 of f of x. That's just the expression I'm using to find the limit. So if you had that in there, that would still be correct, but you don't have to have it substituted in there. And, well, I'll add to that. This is just, again, I'm always thinking ahead to AP. Whoever's grading this question, if this was a question, would see this. So they would see that you took the limit of 1 over x squared. So when you're saying the limit of f of x doesn't exist, they can see that you showed that up here. All right, then for part C, so part C is now a piecewise function. You might notice the top piece is the function we were looking at specifically in part A. So now it's saying f of x is equal to that expression if x doesn't equal 2, so for all x values other than 2, and then if x equals 2, the function is 1. So now we can't use the same reasoning we did in part A because now the function value does exist. So f of 2 does exist now. It's equal to 1. So then here's where you would need to check, does the limit exist at 2? So if I'm finding the limit as x approaches 2 of the function, I'm using the expression x squared minus x minus 2 over x minus 2. And I can use direct substitution. So if I substitute in 2, on the top I'll have 4 minus 2 minus 2, that's 0. Bottom is also 0. So I'm getting 0 over 0.
So we gotta go,
Yes. So I have to rewrite because I have 0 over 0. So that means looking at this, I can factor the top. Okay. So then here's another, I know I said this before. I haven't looked at all the quizzes, so make sure you're doing this. When I rewrite this, I'm not just rewriting the expression, I have to rewrite the limit as x approaches 2 part. Because I haven't taken the limit yet, so the limit still has to be written down. Because if I'm just saying it's equal to this other expression, that's not completely true when you haven't taken a limit yet. So I'm still taking the limit as x approaches 2. The top factors to x minus 2 times x plus 1. I still have x minus 2 in the denominator. And now I can cancel out the factor x minus 2. So I'm really just taking the limit as x approaches 2 of x plus 1. Now if I use direct substitution, 2 plus 1 means the limit is 3. You should write it right away. So now I'm being picky about this because when I was gone last Thursday, I was at an AP conference, the person leading it is somebody who grades AP tests. So if they just see in your work that you're saying this is equal to this without the limit written, and then you write the limit again at the end, you're saying all of those things are equal to each other, but they're really not because you're not rewriting the limit. So if you off to the side, if you didn't put equals here, and you just off to the side, factored it, simplified it, and then you went straight from here to here, that is okay. But it's if you're saying this is equal to something that it isn't actually equal to, they will not give you points. They are very picky, as I've learned. Yes. Well, because your work isn't technically right, if you're not writing the limit. I will not take it off on the quiz, but I'm letting you know for, like, on the test, I'll be looking for that. So I haven't looked on the quiz. I'll just make a note on your quiz. I won't take off for it on the quiz. Okay, back to the point of this problem, though. So function value exists, limit exists. Is it continuous at 2?
Oh, yeah.
Wait, yes, because the function value.
So, well, maybe it was the way I asked it. So I said, is it continuous? No. So is it discontinuous? Yes. So it is discontinuous at 2 because these are different. Or it's not continuous at 2 because the function value and limit are different. So this reasoning would be discontinuous at x equals 2 because the limit as x approaches 2 of f of x does not equal f of 2. Okay, questions on part C? Okay, and then now this one I know I had covered it in the lesson Thursday when I wasn't here. So again, what do these double brackets mean? It's called, yes, you're all right. It's called the greatest integer function, and it means that you're finding the greatest integer less than the number, so whatever it's in between, you pick the lowest. So I want to actually, we're going to talk about D. I'm going to go down to this graph where it says jump discontinuity. This is going to be an example of what's called a jump discontinuity, and I'm going to just sketch this graph. So I did actually, I think I included this graph on the other side as well. Yeah, the graph is also under example 3, but I'm just going to draw a few steps of this function. And if I were to label some of the x values here. All right, so thinking about the function itself, or it might be more helpful if you think about what the graph looks like. Where would you say this function is discontinuous? Okay. At every integer, yes. So at the x value 0, it's discontinuous. 1, 2, 3, it would be. I know I didn't draw the other part. You can see at -1, it's discontinuous. So this is discontinuous at, I'll say x equals n an integer. And then because So what is the reason for it being discontinuous at every integer? Yes. So, and that, I think, Ava, that's what you were saying, that at every integer, your limit does not, well, you could say what you had said, Melanie, but also at every integer, your limit won't exist because you have a limit from the right, a limit from the left, and they're different. But you could say the limit, well, the limit isn't equal to the function value because the limit doesn't exist. So we would say the limit as x approaches any integer n of f of x doesn't exist. The function value at every integer will exist somewhere, but the limit will not. Okay, so then looking at these other two. So a jump discontinuity, graphically what that looks like is any of those piecewise functions where you have one part of your graph and then you literally have to pick up your pencil to get to the next piece of the graph. So it's kind of like you're jumping to the next piece. A removable discontinuity, the first one, well, actually would be like one of the graphs we drew on the front. If I just redrew that one. So a removable discontinuity would be if you just have a hole in the graph. Why it's called removable is the idea is you could make it continuous if you could just fill in that hole. So that's why it's called removable. It's kind of like you're just taking a point away. It would also be removable if I actually had a function value, as long as it wasn't at where the hole is, that's also removable. And then an infinite discontinuity is if you have a asymptote. So this would be one example. But anytime you have a vertical asymptote, there's a discontinuity at that x value. Like this would be discontinuous at the x value 0 because there's a vertical asymptote there. So not only do you have to know how to describe discontinuities using the reasons we were using above, I have also seen AP questions where it will say, would this be a removable, infinite, or jump discontinuity? So you have to know those terminologies as well. And then moving ahead, we have the main idea of continuity down. This is now looking at one-sided continuity. So these definitions are very similar. It's just the definition of the limit from one side. So we say a function is continuous from the right at a number a if, notice the definition is the same, except you're specifying the limit is from the right. So if the limit as x approaches a from the right of f of x equals the function value, then it's continuous from the right. Likewise, from the left, if the limit from the left is equal to the function value. So the only time you really identify one-sided continuity, this only happens if it's discontinuous at a. If your limit from your right or from your left are going to be different, then you would look for the one-sided continuity. So if you want to make a note, you identify this only if discontinuous at x equals a. So if you already know the function is continuous at a, if it's continuous at a, it's going to be continuous from the right and the left. So if it's discontinuous, then you can look further to see, well, would it be considered continuous from one side or from neither side? So I'm going back to the greatest integer function example. For that continuity, here I included the graph. So it said, we already talked about this, where is f discontinuous? I just put that question back on here because it's on a different page. So we said it was at x equals n, where n is an integer, and this was because the limit as x approaches n doesn't exist. The limit as x approaches n of f of x doesn't exist. But now, second part of that question, so I just didn't want you to have to flip back and forth here. You could see it all together. Because it's discontinuous at every integer, we can then say, well, at every integer, is it continuous from the right, from the left, or maybe it's not continuous from either side? So in looking at the graph, let's say I just pick the integer 1. I have, from the left side, that limit would be 0. From the right side, that limit would be 1. Is it continuous from the left or from the right, or neither, would you say? From the right. So it's continuous where the limit is equal to the function value, which is going to be from the right side. How about at the integer 2? Is it still continuous from the right or from the left? From the right. From the left, that function value, or the value is 1. From the right, it's equal to the function value of 2. So at every integer, it's discontinuous, but we can say it's continuous from the right side. So I'll say continuous from the right at x equals n, because the limit as x approaches every integer n from the right side of f of x will equal the function value f of n. And then every limit from the left is never equal to a function value. So it's never continuous from the left side, continuous from the right side at every integer. Questions on that? It's kind of a, well, one that we would more so look towards the graph. I have another example asking the same type of question, but you are not given a graph, you are given a piecewise function. So in example 4, here's the function f of x. It says, where is f discontinuous? Explain why. So that would be like what we did in examples 1 and 2. And then, at any values you say it's discontinuous at, you can then go further and specify, is it continuous from the right, left, or neither? So first of all, where in this function should we check to see if it is continuous? At 1. So we're going to check at 1. Because on the graph, that's where your expression and your graph is going to change, or could possibly change. Does f of 1 exist? Or is f of 1 defined? So f of 1, yes. f of 1, where x is equal to 1, it would be 3 times 1 squared, so f of 1 is 3. So then we have to check, does the limit exist? Now, this function is different from the piecewise functions we had under example 2, because this has 2 different expressions, meaning we need to find the 2 one-sided limits. So we need to find the limit as x approaches 1 from the left side of f of x, as well as the limit as x approaches 1 from the right side of f of x. And again, that's because for our 2 domains, one domain is x values greater than 1 and equal to, and the other is less than 1. So it's domains from the left and from the right side of 1. So if we are approaching 1 from the left, we are looking at the domain for x values less than 1. So we are looking at the expression x plus 4. So this is really the limit as x approaches 1 from the left of x plus 4. And then we can just substitute 1 in. So that would be 1 plus 4, that limit is 5. So from the left, the limit of the function is 5. From the right, we are using x values then that are greater than 1, so our expression is 3x squared. So this limit will be the limit as x approaches 1 from the right of 3x squared. Substitute 1 in for x, 3 times 1 squared is 3. So now putting these together, does the limit as x approaches 1 exist? No. So these are not equal, which means to answer the first question, I can say it is discontinuous at x equals 1 because the limit as x approaches 1 of f of x doesn't exist. And I've already shown in my work over here that the two one-sided limits aren't equal to each other. So then, now at the x value 1, I can go further and say, is it continuous from the left, right, or neither? So my function value is 3. I can see the limit from the right is equal to 3, meaning at x equals 1, this function is continuous from just the right side. So while it's discontinuous at x equals 1, I can then say at x equals 1, it is continuous from the right because the limit as x approaches 1 from the right of f of x equals f of 1. Questions there? Okay. The last part then is talking about continuity over an interval. So up until now, we've just been saying continuous at specific values or discontinuous at specific values. So it says at the bottom there, a function is continuous on an interval if it's continuous at every number in the interval. So we've kind of been specifying where a function is discontinuous. We could then name the intervals where the function is continuous, is kind of what this is saying. So we say here if f is defined only on one side of an endpoint in the interval, we understand continuous at the endpoint to mean from the right or from the left. So I have a last example for you, another graph that didn't copy the greatest, so let me, take a look at what's supposed to be dots and circles here. So there should be a dot here at, what is that, -3, -2 should be a dot. This is a circle. It does look like a circle. If you go to the x value 2 and up to the y value 3, that should be a dot. And then there is a circle at 3, 2, and there should be a dot at 3, 1. Okay, so this question is just saying state the intervals where f is continuous. So I'm just going to make kind of a chart here. If I could spell discontinuous. So I'm just going to locate where is it discontinuous and then state where it's discontinuous. Is it continuous from either side, right, left, or maybe it's not continuous from either side? So where would be an x value where it's discontinuous? -3. Would you say at -3 it's continuous from either side? From the left side? So I'm just going to put left next to it. Okay, and then another x value. It is discontinuous at 0. That would be an infinite discontinuity. Is it continuous from either side? No, so I'll put neither. And then another x value. 4 is one, 2 is another. So at 2, is it continuous from either side? From the right? How about at 4? Neither. Any questions on that part? If you have a question, yes, we are going to write it in interval notation, and then I'm going to talk about the interval notation. So in interval notation, naming then the intervals where it's continuous, and how you're going to write this with parentheses and brackets, you are going to use a bracket to show that it would be continuous from that side. So what I mean by this is my first interval is, and I'm assuming this is continuing, these are kind of showing horizontal asymptotes almost there. So negative infinity up to my first x value is -3. Now it is continuous from the left side. So on this first interval, I should have a bracket and then the union symbol. The next interval is starting with -3, but should have a parenthesis because it's not continuous from the right. So this would show at -3, it is from the left, not from the right. So -3 up to 0, 0 is discontinuous on both sides. So both sides of 0 should have parentheses. 0 up to 2, 2 is continuous from the right. So I would have 0 to 2 in parentheses, union, and then the second interval that includes the 2 would have a bracket, or would start with a bracket. And then 2 to 4, 4 is not continuous from either side, so parentheses on each side. And then it ends with 4 to positive infinity.
Why wouldn't the second one be a bracket? Because
There is, but the limit is still where the circle is.
okay.
So the limit, even though the function value exists, both limits do not equal the function value. Because 2 is continuous from the right side, so this would show from the left it's not continuous, but from the right it is. All right, one comment. One comment about this interval notation. These are the intervals for, or this is the interval notation for continuity. What does this remind you of finding? Domain. So what we are going to continue on with tomorrow is we can kind of simplify this a little bit by saying certain functions are continuous on their domain. And what that means is when you are determining where a function is continuous, it's basically just asking you to find the domain. So making that connection between continuity and domain.